Okay, so we talk about the interfacial energy and the impact on the shape of the so-called precipitate. Some secondary phase coming out from the so-called primary or matrix phase. Okay, if they are completely coherent, if they are completely incoherent. Okay, now let's deal with some case which is kind of in between these. Partially coherent precipitate. Okay, so we have, let's just read this. Beta precipitate coming out from alpha phase, right? Alpha is your matrix, beta is your precipitate coming out. Both we are dealing with in this course solid material, okay? And but with good match along one particular crystal plane or particular interface, okay? For example, we give it here. We give the example here. We have on the right is the unit cell for pure alpha aluminum. What structure? On the right side? Well, cubic, right? 4.04, 4.04, but with what? Face center. So the typical aluminum is IFCC, very soft material. Okay? And then if people put copper into the material, they may form a so-called theta prime precipitate. A copper aluminum alloy with certain crystal structure. Okay, now look at this unit cell for this so-called theta prime versus the FCC aluminum unit cell. Okay, look at the base. The unit cell for this theta prime, is that cubic or not really cubic? The unit cell for this theta prime, is that unit cubic or not cubic? Not cubic, right? The base is a square, 4.04, 4.04, but the height is 5.8, right? It's not really a cubic unit cell. But at least at the base plane, you see for both of the so-called 001 plane, and the 001 plane for the theta prime would be parallel, and actually you can arrange it exactly the same as 001 for the alpha aluminum. Make sense? If I call what is 001, if this is my 100 direction x, this is y, this is z, the 001 plane is just the base plane, right? The bottom base plane or the top plane. They will look exactly the same packing. Make sense? With the same length. Okay, and I can match the close packing direction. Make sense? For this 001 plane, 001 plane, this so-called 110 from the origin to the opposite corner on the same plane, I can have matching of the close packing direction. Make sense? So 100 match 100, 110. Actually, I should probably say 110 match 110 here. Okay? So this would be the preferred plane. When these two planes would match, if you have to guess, what about the interfacial energy? High or low? If I have match of this 001 plane for theta prime versus 001 plane for alpha aluminum, at that interface, the have to be low, right? Because I'm not really breaking many bonds. They match pretty well. Okay. In this case, the shape for such a precipitate, if there's no other matching plane, let's say the other crystal plane, they have terrible match. We cannot try to match, as you can see here, literally right? For the side plane, difficult to match. The symmetry would change. So if there's no other matching plane, quite often they will take the shape of a disk. What do we mean by disk? It's kind of a cylinder, but it is very low of height, very large diameter. That's what we mean by a disk, right? Quite often by a disk. So we don't have it here, but if people are going to draw the so-called contour plot, the gamma plot with respect to orientation, gamma represent what? Interfacial energy between the two structure. Okay, the gamma, of course, when we originally did this, it was for surface energy, but here it's for interfacial energy. If we plot the gamma versus orientation, okay, we get something like this, like 2x together. But then when we said, okay, once you have the so-called gamma contour plot, you can get the so-called equilibrium shape of a crystal by so-called Wolff construction. And what is Wolff construction? It's kind of like from the center to any point on this contour plot, and then you draw a, not a tangent, a perpendicular plane, and the inside cut of all those planes that will define this blue shape, which is our equilibrium shape. From here, from the center to this point, you draw a perpendicular plane. Okay, from here you draw a perpendicular plane. For every point, you draw all those perpendicular planes and the inside of all those that would cut out such a shape called that's your so-called Wolff construction that determines your shape, which means, okay, it's a disc shape types of the precipitate. In this case, if there's one good matching in one type of crystal plane but no matching in the other, it will take this disc shape. Okay, and from contour plot, from the center to the contour plot to one end, that gives us the gamma C. What does gamma mean? Interfacial energy, C for coherent. That is your coherent interfacial energy. That distance, remember on this contour plot, the distance represents what? The contour gamma plot, the distance from the center to any point on this red dashed line means the absolute value for the interfacial energy. So from center to here, that's my smallest interfacial energy, which is C for that this particular coherent plane between this 001 plane for theta prime and the 001 plane for alpha aluminum. Okay, and then the large one, gamma I for incoherent. That gives us the incoherent interfacial energy. Make sense? Larger. The distance is larger means that energy is larger. Okay, and then of course, if we define the R as the radius for this precipitate, we said it's a disc shape, shallow disc, R for its radius, H for height of this shallow cylinder, okay, or this disc, and geometrically, the equilibrium shape of this disc has to satisfy certain relationship. Under what condition? Equilibrium. Under equilibrium, which means you are trying to minimize the summation of the total interfacial energy. The geometric relationship would have something like this: 2R over H equals gamma I over gamma C. Okay? And it just tells you that certain relationship between radius and the height. Based on this relationship, if gamma I is much larger than gamma C, what does that mean? If gamma I, based on this relationship, if gamma I, the incoherent is much larger than coherent, what would be the geometrical consequence? The 2 times of radius is much larger than height. On the other hand, if gamma I is very similar to gamma C, what does that mean? If gamma I is very similar to, which means coherent intercoherent doesn't matter, then what happens to the shape? The radius, the 2 times the radius, which is the diameter, and the height is pretty much the same. That makes sense, right? If they are similar, they look more and more like a cube or even like a sphere. Make sense? If the individual energy, all this plane versus that plane, they are pretty much the same, then of course it looks like dimension-wise, it looks like pretty much like a sphere. Make sense? That's what this relationship is about. Okay. If there is other matching planes other than this one plane, there may be other plane, then the precipitate would take some other shape. Okay. So now I have this one slide to prove kind of a mathematical proof for that relationship. Okay, between this so-called plate-shaped precipitate, the relationship between radius or diameter and the height with respect to the ratio between the interfacial energy. We said the total interfacial energy for this such a plate-like, or by plate we mean a flat or very thin cylinder. Makes sense? That's just geometrically worded. The total interfacial energy would be, I write it as this. Does this make sense? G for, in this case, total interfacial energy is sigma of A I gamma I, or as I written AJ gamma J. AJ means what? The area for J, for number J interface. Gamma J means the interfacial energy for that particular J interface. And in this case, I write it as this. 2 pi r square, what is that? Pi r square is the surface, it's the area for the cylinder top surface or the bottom surface. But since we have both top and the bottom, we have the factor of 2 here. Times what? We said the coherent one is the top one and the bottom one. Make sense? It's a plate that the flat one. Okay. And the 2 pi RH, what is that? It's the side, the cylinder side total surface area, right? 2 pi r is the circle circumference length times h. That's like when you expand it out. Okay, times what do we say? Gamma I. We assume the side interface is what? Incoherent. Make sense? This add up together is my total interfacial energy. And what do we want? For a fixed precipitate, we said, okay, it can take a very tall cylinder. It can take a very thin, narrow cylinder. But in this case, what is fixed? The total volume is fixed. Make sense? A fixed amount of precipitate. It can take a very thin, long cylinder, tall cylinder, versus the same volume can become squeezed into a very flat plate. In this whole process, the total volume doesn't change. The total mass doesn't change. The total molar doesn't change. But the interface may change. The relative interfacial area also change. Okay, which means what? Pi r square h equals V. What does V stand for? Volume is a constant. Make sense? I'll put another way. If we are going to represent h as a function of V and R, remember V here is a constant. So h for the height of this cylinder is the total volume divided by the area, right? Normal cross-section area for the cylinder. Okay? Then the total interfacial energy now becomes what? We now replace h with this guy, right? So we are going to rewrite it as the total amount of interfacial energy is first term we keep, right? The second term 2 pi r we keep, but h now replaced by V volume over cross-section area times gamma I. Make sense? And then of course this pi r and pi r would cancel. We have 2V over r times gamma I. Make sense? That's what we have. Now, under equilibrium, we want this G to what? Reach minimum, not zero. No, zero. You cannot, the zero means you have to interfacial area goes to zero. It never goes to zero. But we want equilibrium. We want most stable, reach the so-called minimum value. Okay, and mathematically for G to reach minimum value means what? The first derivative of this guy has to be zero. Of course, if you want to be precise, minimum means the second derivative has to be positive. You can check that. But at least, okay, let's first look at only the first derivative. It got to be 0. And that's what we have. Check if this is correct. The first term, 2 pi r squared gives us another 2. So 4 pi r times gamma c, right? That's the first, the order derivative of the first term. The second term, 2, I keep 1 over r become minus 1 over r square, and v we keep times gamma I equals 0. Make sense? That's your first order derivative equals 0. And as a result, we are going to rearrange this. Make sense? We are going to rearrange this. And do you have this? 2 pi r gamma c equals what? 2 times v divided by r square ri. And again, don't forget the v is what? V is a constant, but V in this particular case is just the area, 2 pi r squared times what? H. And as a result, what would cancel? R squared would cancel. So we are going to have 2 pi h gamma I. So we have something on the left, something on the right. Something on the left has R for radius, gamma c for interfacial energy for the coherent interface, and h for height of this cylinder, gamma I for the interfacial energy for the incoherent interface. And in here, we further simplify. We would get what? 2r over 2r gamma c equals h gamma I. Make sense? Or write it in another way. 2r over h is gamma I over gamma c. Makes sense, right? That's just how mathematically, okay, we get the relationship. How well does it come from? You can just derive it by making certain assumptions. The total volume doesn't change. And then it can take different shape. It can take the shape of a very tall cylinder or a very shallow, low cylinder. But which one gives us the so-called minimum interfacial energy? We take the first derivative, make it 0, and we get it. Make sense? Okay.